Pretty quick, right? I mean, of the implicit differentiation problems, this is probably the easiest, right? There's nothing super tricky going on. All right, so let's see, we take the derivative of both sides, so that's going to give us 2x plus 2y dy dx is equal to 0. Now I get dy dx by itself. So dy dx is going to equal, can just go ahead and say that's negative x over y. All right. We good with that part? Because I think there were probably a couple of problems at home that made you do it. All right, so, all right, that's not the goal today. The goal today is take the second derivative. All right, I want to find the second derivative. Okay. Well, how do you find the second derivative?
Quotient rule?
Yeah, well, you take the derivative of the derivative, right? Is everybody okay with that part? I mean, that's how you find the second derivative. You take the derivative of the derivative. So now I have to take the derivative of this and quotient rule, right? So we start, so let's see, the derivative of the top is -1 times the bottom minus derivative of the bottom, which is dy dx, times the top, which is -x, all over the bottom squared. I mean, I can clean it up a little bit.
Wait, so the derivative of y, is it y dy dx?
Well, the derivative of y is 1. And then because you took the derivative of y, you have to put a dy dx. Or, all right. Or you could think, well, just the derivative of y is dy dx, right? Derivative of y with respect to x. All right, so I mean, if I clean it up a little bit, I end up with -y plus dy, actually, I'll go ahead and say that's x, dy dx, all over y squared. Yay, but I'm not done, all right? I don't want dy dx in my answer. Is everybody okay with this part? Okay. So to find the second derivative, okay, that makes sense. You take the derivative, second derivative, you take the first derivative. That's what you do. So I've got the second derivative, but your final answer can't have dy dx, right? I mean, like yesterday, we just got used to the fact that we can have our derivative be defined in terms of x and y. That's what happens with implicit differentiation. And so my second derivative, I want defined in terms of x and y. I don't want dy dx. I really wish I knew what dy dx equals. I mean, if I had something that told me what dy dx equals, then I could replace dy dx, my subtle hints, right?
Oh, you're talking about
Yes, you do, right? Like my subtle hints, right? I need to know what dy dx equals, right? Okay. So, right? Because then if I replaced it, then I don't have dy dx in my answer, do I? All right, so you go through. Let's see, so that's going to give me a -y plus x, but instead of dy dx, I get to write down what it equals, which is -x over y all over y squared. Okay. Of course, now I have to clean it up, right? So how does that clean up? It's not terrible. I'm going to hear some moaning, and I think most of you are going to moan at the next couple of steps. Some people are going to say, "Well, that's kind of neat," but here we guess I better get through with it, right? So let's say that's a -y minus x squared over y all over y squared, and surprise, surprise, I don't want this layered fraction stuff. These are the markers that are writing. Okay. So the trick is, I don't like this fraction here. So my trick is I'm going to multiply top and bottom by y. And if I distribute that, I go off the screen. I need a little bit longer. Okay. And so if I distribute this, that's going to give me -y squared minus x squared all over y cubed. Right? That's not the part that I think I'm going to hear some moans about. Okay? It's kind of straightforward, like fairly typical of what's going to happen with algebra stuff, all right? We've gotten rid of the fraction, you say, hey, I'm done. And most of the time you are done. Right? At most of the time you're done at this stage. But this is one of these cases where we can simplify it a little bit more. Do you have to simplify it this little step when you have to find the second derivative? 90% of the time, no. This one's simple enough that we can make one final simplification, right? We can do one final trick to make this a little bit more compact. And the one final trick is, well, first, I'm out of root, so I'm going to write up here. I'm going to factor out a -1, so it's going to be a negative y squared plus x squared all over y cubed. Right? That's not scary. And my challenge is for you not to groan at the next step. Okay? That's my challenge, right? Can we not groan at the next step?
Yes.
The next step is not hard. I just don't want you to groan. Huh. Y squared plus x squared. I've seen that somewhere before. Oh, here. What does y squared plus x squared equal? Oh, so this is equal to negative, that's a 25, so I get negative 25 over y cubed. Thank you for not groaning.
That's a long problem.
Oh, okay, let's go back and unpack what we did, right? It's a long problem, mainly because I'm long-winded and I kept talking through the whole problem, right? Okay. I like talking, and so I talked. That's why it took a while, right? But what did we do? Well, find the second derivative. Well, if you're asked about the second derivative, well, it makes sense you take the first derivative. Well, that's what I made you do yesterday, right? So taking the first derivative isn't terrible, particularly in this problem. And then to find the second derivative, well, it makes sense you take the derivative of the derivative. So we did, right? We took the derivative of the derivative, and the rules haven't changed. If you take a derivative of y, you got to put a dy dx because it's implicit differentiation. And so we end up at this stage, and you cannot have dy dx in your final answer. So then the trick is, okay, you find out, well, what does dy dx equal? Oh, we've already figured that out in part A, almost. Plug it in, and then clean up. Now, for the most part, you end here. Most of the time when you do a second derivative, you do the cleanup, you're done. This is one of the cases where you can go one step further. A lot of times you can't. It's ugly. And now, in taking the second derivative with implicit differentiation, I learned this the hard way the first time I taught it. A lot of times I just make up examples when I'm practicing taking derivatives because it doesn't really matter, right? You just, like, if you think about just practicing product and quotient rule, I just put random stuff on the board. I'll guarantee second period has different problems than sixth period because I don't have them written down. I just put something up, right? For problems involving second derivative with implicit differentiation, you got to be pretty careful. You just can't put something random. Because if I put something random, like, this is a pretty simple derivative, isn't it? Right? And the derivative of that got kind of ugly. Not too bad, but got kind of ugly. If this thing was any ugly, if the first derivative ended up being ugly, when you try to take the derivative of that, it blows up. And so you have to be careful. And like Dr. Nguyen, he's assigning problems out of the textbook today about the second derivative of, and I don't like the books and the problem. I don't like the problems in the book because, like, of the 6 problems that are dealing with finding the second derivative, 4 of them are okay. 2 of them are absolutely hideous. I mean, they would fill up this entire board to do the second derivative. So I'm not assigning those. But do you understand the procedure of what you're supposed to do to find the second derivative?
Yeah.
Okay. Are you going to have to do it? Yes. Is it on the AP exam? Every year it's a multiple choice question. Without exception. Yeah, just one. It's always, sometimes it's and these are the two ways it's asked. Method one is, they say, here is your relation, find the second derivative, and so you have to check the appropriate box. Most likely what it does is they say, given this, compute d2y over dx squared evaluated at the point 3, 4. So that means you actually have to take the second derivative
And then,
and then plug in. But the benefit of simplifying it here is it's real easy. You just have to plug in the y value. Had you stopped here, you have to plug the x and the y and make sure you got the signs right. Okay. All right, so what do I want to do today? I'm actually kind of excited because I can show you what a free response question looks like. So for those people at home, in OneNote, if you look in the notes section, not the homework, in the notes section, you'll see something that says free response.
Thank you.
And let's put this back. Oh, I should have hit pause. Oh well.
well, these problems are 22 years old. That's older than 21 years.
That's a profound statement. Okay. So I do apologize for folks in the virtual world. These are in reverse order in OneNote, so scroll down to the bottom. And I kind of want to, first I want to tell you about a little philosophy about free response questions on the AP exam. And then we're actually going to start this. All right, so here's how free response questions work. Of the 6 free response questions, I'm usually pretty good about predicting 4 of the 6 questions. Because it's not just me. I mean, if you just looked at the last 20 years, you'd say, you're going to have one like this, one like this, one like this, one like this, right? It's not hard. It's not like I'm really smart at that. It's just, you just look at a pattern, it's obvious, right? So, I mean, I'm with 90% certainty, I can say you're probably going to have, these are going to be 4 of the 6 questions, right? Now, what's different is they tweak it every year. See, what happens is they give a question. So they give a question about implicit differentiation, which is what this is. And here's what good calculus teachers do. Or if you're teaching an AP calculus teacher, even if you're a bad one, right? You say, all right, they asked this type of question. They asked this type of question last year. I want to make sure my students know how to answer that question, right? And so you train them. You train your students, right? This is how you answer that question from last year. Well, the people that write the AP exam are really smart. And they know that teachers have prepared students to answer last year's question. And since they're smart and they want to make sure that they challenge the student, they go, well, how can we tweak it? So that's a little different, right? Fully expecting that the teachers have taught how to do every detail of last year's problem, right? Well, and the same thing happens the next year, and then the next year, and the next year. And so what happens, even though I can predict that 90% chance you're going to have a related rate, you're going to have an implicit differentiation problem, it's been tweaked over the years. Can you imagine? So the difference at an implicit differentiation problem was 20 years ago, right? After they've done 20 years of tweaking, right, it's going to look a little bit harder than it does. Like an older problem is going to look easier than a newer problem because you have all these smart people every year changing it. Does that make sense? And so what I have here is almost a snapshot of a progression of one particular type of problem. Here's an implicit differentiation problem. I have 3 questions, right? These are 3 complete questions, and we can actually answer all parts, which is kind of rare, right? And the first one I'm going to talk about is from 1998, then I've got one from 2000, I have one from 2008. And they're all measuring the same information, but so we're going to talk about how to do it, right? But you're also going to get to see how the problems tend to get a little bit harder as the years progress. Like if we look at some really old free response questions after we've, like at the end of the course, we look at really old free response questions, you might look and say, well, how did everybody not get 5s, right? Because they're going to look so much easier than the problems they're giving today. So, but that's all because things are progressing. And all right. All right, so here is this is a very typical way that they ask implicit differentiation. So if I look at 1998, it says consider the curve defined by blah. It says show that dy dx equals this. Did they use the words implicit differentiation at all in this problem? No, and they're not going to. Do you have to use implicit differentiation to take the derivative?
Yes.
All right, so just for laughs and giggles, everybody take the derivative. We're going to do part A. Okay? And I'm going to remember to press pause. You don't get many points for it. Usually, so a free response question is worth 9 total points. Usually this verification is usually worth 1 point, at most 2. But did everybody get this?
Yeah. Well, I got a 2xy, negative 2xy plus 4x.
Oh, that's the same thing.
Okay.
Yeah. If you wrote negative 2xy plus 4, that's the same thing. Yeah, you've got full credit, all right? All right. Now let's talk about B, because this is pretty common. And it says, write an equation of each horizontal tangent line to the curve, right? So how do you find a horizontal tangent line?
You can find
Well, what do we want our slope to be?
0.
We want our slope to be 0, right? Everybody okay? Horizontal tangent line means I want my slope to be 0. So if I want my slope to be 0, well, let's see. If I'm looking at dy dx, so, well, I've already got it here. I'll just say I want this to be 0. How do you make a fraction 0? What? The top is 0. Right? So if you want your slope to be 0, right, I want the top to be 0, meaning for part B, I want 4x minus 2xy. I want that to equal 0. Right? Okay, so what does that mean? Don't know, right? Well, pretty much anytime you set something equal 0, the way you kind of your philosophy, the philosophy is you set equals 0 and hope you can factor. Well, I can factor this. So when I factor this, I'm going to factor a 2x out, so that's going to give me what? 2 minus y is equal to 0.
Yeah.
Okay, so I get 2x, 2 minus y is equal to 0. Well, and kind of the sort of the logic is, well, that means I want this to be 0 and I want this to be 0. Okay? So for this to be 0, so if I want 2x to equal 0, that implies that x is 0. And if I want 2 minus y to equal 0, that means I want y is equal to 2. All right. Says, write an equation for each horizontal tangent line to the curve. So here's what we have. I'm going to move this over. We have 2 situations. We got one situation where x is equal to 0. Now, I know for me to find horizontal tangent lines, I need, I need a point. If x is 0, I need to be able to figure out what the y value is. Okay? So if x is 0, how do I figure out what my y value is? Plug it into what? Perfect. You plug it into the original function, right? You think, well, that's really ugly, but when x is 0, it becomes less ugly, doesn't it?
Yeah, you just have 2y cubed plus 6y.
Well, it's 1, right? So when x equals 0, that's going to give us 2y cubed plus 6y equals 1. All right. I finally remembered. So as far as calculator use on the AP exam, Currently, the first 2 questions are calculator and the last 4 are non-calculator. Before, I forget, 2000, it used to be the first 3 were calculator and the last 3 were non-calculator. 1998 was an anomaly. I think 1998 you could use your calculator for every single question. Because if you can't use your calculator, you ain't solving this. Right? I'm not going to worry about solving. I'm just going to go ahead and tell you that to use your calculator, you would find that when this happens, y is going to equal 0.165. I've already done the work. Right? This question is never a calculator question anymore. Right? And you're going to see in the other one. All right? So, so what we have was when x equals 0, y is going to equal this, right? That's the point. And now this is this is a theory part. If y is equal to 0.165, does my slope equal 0?
No. Right? It could.
What? Oh, actually, no, at this, so at x equals 0 and y, no, that's right. So what we have is that when x equals, so I know that my slope is 0 when x is 0, so I've got some weird graph, right? This thing's some sort of wacky looking graph. It's got little circles or whatever, right? And I know that the slope is 0 at the point 0, 0.165. Write an equation of each horizontal tangent line to the curve. Well, horizontal lines like y equals a number. So if it's horizontal at this, what's my equation of the line?
Y equals 0.165.
Y equals 0.165.
Oh.
And so that's one situation, right? That's one horizontal tangent line. What's my other horizontal tangent line?
When you plug in y.
Y equals, well, no, we already know y equals 2, don't we?
Oh, that's the other.
Yeah, that's the other one.
Would we only need one or both of them?
You have to put both.
What is this right hand equation?
Of each horizontal.
Oh.
That each, okay. All right, next algebra thing. It says the line through the origin with slope -1 is tangent to the curve at point P. Find the x and y coordinates of point P. That's a lot, isn't it? Okay.
Not doing the second.
Well, the second line was y equals 2, wasn't it?
Oh, I see.
Like we're looking for y equals a number, right? Oh, look, y equals a number, right? Actually, technically, we should plug the 2 in to make sure the x value is valid. That's actually going to show up in the next problem, but it does work. I really want to talk about this because these are some algebra tricks that I don't think you've seen that are required to answer these questions. All right. So it says the line through the origin with slope -1 is tangent to the curve at point P, and so they're basically saying we've got a tangent line, right? And it's tangent at a certain point P. Okay, find the x and y values at point P. This is a hard algebra question, right? It's really hard if you haven't been shown how to do it, right? So it's kind of my job today. Trying to show how do you handle this. What's the equation of a line through the origin with slope -1?
Will you repeat the question?
It talks about this thing. It says the line through the origin with slope -1. What is that?
Y equals -x.
Y equals -x, right? Everybody okay? I mean, imagine, here's your picture, right? Slope through -1, right? What's the equation of that line? Y equals -x. all right? So, I'm running out of room. So we have this expression, y equals negative x. And what we need to do is we got to figure out what x and y are. How on earth do we figure out what x and y are? Well, that little line, y equals negative x, there's two ways we can, well, we know two things. We know y equals negative x, and we know that our slope is equal to negative 1, right? And because that's the slope of the tangent line, so my slope of the tangent line is negative 1. If you know the slope of the tangent line is 1, what equation can you give me?
Y equals, wait, what?
It's hard. I haven't made you do much of these, which is why this is hard. If you know the slope of the tangent line is negative 1, what equation could you give me that uses negative 1? If the slope of the tangent line is negative 1, what is slope of the tangent line? The derivative. What equation could you give me? Derivative equals negative 1. Does that make sense? Okay, if they tell you the slope of the tangent line is negative 1, right? Right, remember, slope of the tangent line is code for the derivative. So any expression that you have that says derivative, right, and if you want your derivative equal negative 1, I can set my derivative equal to negative 1. That's an equation I can write. All right, so I'm going to write that equation. So if I write that equation, that's going to give me 4x minus 2xy all over x squared plus y squared plus 1. I want that equal negative 1. And I have a problem, right? Good luck solving that, right? It's like I need something else. Right? I can't solve this because it's got x's and y's.
Oh, you turn all the y's to negative x's?
I need something that converts y's to x's. See? I need another equation.
Oh.
Well, I said it was hard. It's really hard if you hadn't had someone try to teach you how to do it, right? So this says y equals negative x.
Would you make the y's x's or the x's y's?
I would change it all to x's.
X's.
Yeah, I think your life's going to be a lot easier if you change them all to x's. So actually, the way I would solve this, the first thing I do is I don't like fractions, so I'm actually just going to move this over. And so that's going to give me 4x minus 2xy is equal to a negative 1 times x squared plus y squared plus 1. And now I get to use, okay, where I see a y, I'm going to write negative x. So this is going to give me 4x minus 2x equals negative 1 times x squared plus another x squared plus 1. And I need to plug in my negative x. So I get 4x plus 2x squared minus, or equals, it's going to give me, that's 2x squared plus 1, so minus 2x squared minus 1. And I get 4x squared plus 4x plus 1 is equal to 0. It's going to factor as 2x plus 1 times another 2x plus 1. And so I end up with x is equal to a negative 1/2. Yay!
Wait, how do you know the y though?
Yes.
Isn't it supposed to be x squared plus y squared plus 1?
What does y equal?
Oh.
All right. So I got x equals,
And then you plug the x equals negative 1/2 back into the equation.
I just plug it into this one, right? That'd be easier, wouldn't it?
Yeah.
I mean, if you want to, you can plug it back in if you want to, but
No.
no, I'd rather not. I'd rather just plug it in here.
So y equals 1/2.
So y is going to equal 1/2. Find the x and y coordinate of point P, which is going to be negative 1/2, comma 1/2. Now, maybe I should bring up the rubric for this. So part A was a lot easier than parts B and C, weren't they?
Yes.
Weren't they a whole lot easier? Now, okay, more bad news. We're not going to learn anything else the rest of the year that's going to make part B and C any easier. Yeah. Because everything I've talked about today, it's got a little bit of calculus, but there's a lot of just algebra stuff that you have to know. Right? So there's no calculus. There are some things where there is some calculus that's going to make some things easier later. Like there's some things we're going to learn that's going to make, like remember when we did like the definition of derivative, then we learned like the power rule. So that made taking the derivative a whole lot easier. Right? So there are things that we're going to learn in the future that's going to make some of the stuff we've been doing easier. This doesn't get easier. There's nothing I'm going to teach at any chapter in the future that's going to make this problem any easier. Right? So that's the other thing. That's one thing. The other thing I want to sort of talk about on this problem is how much work did someone do to create this where you end up with nice answers? Can you imagine trying to create a problem? Like, look what we did. We ended up with something that factored nicely. It's hard to do that. I tried. What I do is like we practice free response questions, and then I think, okay, on a test, I'm going to create my own free response question that comes out with nice answers. It's really hard. So I mean, just from a teacher's perspective, I'm always impressed with almost some sort of elegance. I realize this is the first time you've seen this, and yeah, there's a lot of tricky stuff. Yeah, I'm not denying there's tricky stuff. Like to recognize you have to write y equals negative x and then to plug that in, right? Or you take this and set it equal to negative 1. The other thing you could have done is you could have used this equation. If it says x equals negative 1, if it says y equals negative x, you could replace the negative x up here. And God, does that work out? No, I think it's kind of ugly. I think you end up with something that's hard to factor. But yeah, there's this part. All right. So there's our first free response question. That's strictly implicit differentiation. Now let's look at 2000. Let's see what changed from 98 to 2000. I realize the bell's about to ring. Your homework I gave, like you guys, if you look on the back, that's your homework. And it's just practice, right? It's more practice of implicit differentiation. It's got some it's asking you to find the second derivative. It's asking you to take the second derivative and plug in points. And then it says find the equation of tan. Don't worry about the normal line for 10 and 11. But I'll post answers for that. And we may not finish this. In fact, I'm fairly certain we won't finish it. But I do want to talk about the similarities between this problem and the previous one. So, consider the curve given by blah. Show that. Virtually the same question, right? Just change the numbers, da-da-da-da. Now, here's how they tweaked it. It says find all points on the curve whose x-coordinate is 1 and write down the equation for the tangent line. What do we need to do in part B?
Would you solve for the original equation?
I wouldn't solve. If I want to find an equation of a line, what do I need? Point and a slope, right? Right? They gave me x. I need a point. How do I find the y?
Plug in x, 1.
Plug the 1 into the where? Into the original equation, right? So we plug the 1 into the original equation and we solve. It turns out when we do this, we're going to get two y values, right? I'm going to do this complete problem tomorrow, but I want to make sure I have enough time to talk about the whole problem. as opposed to only 2 minutes. And then, once you find the x and the y, then you can plug it in here to find the slope. So you've got your slope and your point. There end up being 2 lines here. Now, I do want to talk about this. It says find the x-coordinate of each point on the curve where the tangent line is vertical. So the previous question, they talked about the tangent line being horizontal. So a tangent line being horizontal means your slope is 0. If your tangent line is vertical, what does that mean about your slope?
Undefined.
It's undefined. So what has to happen?
It's zero.
Bottom is 0.
The bottom is 0. And so we set the bottom equal to 0. And then there's some algebra tricks involved in that.
You do the same thing as part B from 6, just make the bottom 0 then?
Yes. Yeah, you'd set the bottom equal 0. So they have kind of the 2 ways they ask about, you know, tangent lines. They talk about horizontal tangent lines and they talk about vertical tangent lines. All right.